Let's make a homogeneous mixture, a solution, from two components, water and ethylene glycol. Both of these substances are liquids at room temperature, so we will be making a solution from two liquids. Water has a melting point of 0 degrees C and a boiling point of 100 degrees C. Its vapor pressure at 20 degrees C is 17.535 torr. Ethylene glycol, on the other hand, has a lower melting point of minus 12.9 degrees C and a much higher boiling point of 197.3 degrees C. Its vapor pressure at 20 degrees C is 0.06 torr. Clearly, these substances have different physical properties, as we expect. If we make a solution from these two components that consists of 50% ethylene glycol and 50% water by mass, the resulting solution will be a liquid at room temperature, just like the components. We can then measure the physical properties of the solution. If we do this, we will find that the solution's melting point is minus 36 degrees C, its boiling point is 109 degrees C, and its vapor pressure at 20 degrees C is 12 torr. Notice that the solution melts at a lower temperature than either one of its components, and that it boils at a temperature slightly higher than that at which the water boils. The vapor pressure of the solution also does not match the vapor pressure of either one of the components. This happens for other physical properties as well, such as surface tension, viscosity, refractive index, thermal conductivity, and electrical conductivity. This is somewhat remarkable because the formation of a solution involves no chemical changes, and yet the solution in this case has very different physical properties than the components that were used to create it. And it appears that the solution's physical properties are not a simple average of the properties of the components. We are going to be interested in the observation that components of a solution have well-defined physical properties, but that the physical properties of the solution are different than those of its components. We are going to answer the question, how can we predict the properties of solutions from the properties of its components? We'll focus on the physical properties of boiling point, melting point, vapor pressure, and osmotic pressure. These physical properties of solutions are called colligative properties. They change as the quantity of solute in the solution changes, but they change in exactly the same way regardless of which solute is added. Physical properties of solutions that depend on the identity of the solute are called non-colligative properties, or sometimes additive or constitutional properties. Examples of these include taste, color, viscosity, and surface tension. Along the way to understanding how these properties of solution differ from those of its pure components, we'll also need to learn about how solutions form, the energy changes during solution formation, and the factors affecting solubility. You might wonder why we bother studying these properties of solutions. Well, aside from their importance in better understanding the behavior of chemical systems, they have a wide range of practical applications. The change in boiling point of a solution relative to its components is utilized to provide a heat transfer fluid for a car engine that does not boil away when the engine runs. The osmotic pressure of solutions is relevant when thinking about desalination, the process of removing salt from seawater to provide drinking water. It is also relevant in plant structure and function, and generally maintaining cell integrity in a wide range of organisms. The change in freezing point of a solution relative to its components has application in providing a heat transfer fluid for a car engine that does not freeze in cold weather when the car engine is not running. It is also relevant to melting ice on roadways at temperatures below the freezing point of pure water. And finally, plants utilize freezing point changes upon solution formation as one mechanism to help prevent the freezing of their cells, and hence their death, in winter. The change in vapor pressure of a solution relative to its components is important when thinking about distillation and modeling the world's climate. There's no way to properly model world climate without an understanding that water evaporates more slowly from seawater than from pure water. And that's Introduction to Properties of Solutions.